Okay, so let's imagine that we have a universe that is filled with charge, and the charge density is rho star everywhere. And we want to find the value of the electric field. Let's say, I don't know, this is an x, y, and z out of the page coordinate system. We want to find the value of the electric field at some distance d directly above the origin. So we can imagine using Gauss's law for this, and that means that we have to identify a symmetry. So we really have to address the question, how is this charge density, how is this constant charge density generated everywhere? And the answer is either we take little spheres and with constant surface charge density, and we grow the universe that way by filling it with these shells. And so we have to integrate over all these shells, an infinite number of shells, to create this. That would generate a spherical symmetry. We can imagine cylinders, right? So infinitely long cylinders that are used to build this uniform charge density everywhere. Or we can imagine putting planes one on top of each other, right? So infinitely large planes that that fill the entire universe with constant charge density rho star. In this case, we would have planar symmetry. So we'll see that the value of the electric field here, if we assume that we build the universe this way, is going to be less than if we assume we built it this way, which will be less than if we assume we built it this way. And the reason for this is that there are there's no infinity here. There's one infinity assumed from the start here, because we're building it with an infinitely long cylindrical shells of charge, and the same. And here we have two degrees of infinity, right? We have a plane, so we're building it from the start with two infinities, and so we'll have a stronger electric field, increasingly stronger electric field here. So let's show that. So let's say we want to use Gauss's law. We built the universe this way, so Gauss's law would say left-hand side electric field times, it would be spheres, right? So spheres that have symmetry. So we want the electric field here, so we have a sphere of radius 4 pi, a sphere of radius d, and so the left-hand side is we integrate the field over that surface, that sphere, and it looks like that, and then the charge inside, it's distributed over the volume, right? So it's a volume charge density, so we have a 4/3 pi rho star times d cubed over epsilon naught, and that gives us an electric field that is pointing that way, which is rho star d over 3 epsilon naught r hat. Let's assume we built it using infinitely long cylindrical shells. In this case, we want to find the electric field d, so we are integrating over a cylindrical shell of radius d. So the left-hand side of Gauss's law looks like E times 2 pi d times h. We make it some h long. The right-hand side is the total charge there. It's distributed over a volume, and that volume is pi d squared, right? The area of the disk that closes the cylinder, pi d squared times h, and we divide that by epsilon naught, and so we get an electric field that is pointing straight up, which is rho star d over 2 epsilon naught r hat cylindrical. So this electric field, we can see that it is in fact a little bit stronger than the electric field produced, assuming this symmetry, spherical symmetry. And let's say we build the field, we build this universe with planes of charge. In this case, we would have planar symmetry. And so we would have a top surface and a bottom surface, and the total distance between the top surface and the bottom surface would be 2d. So, so we have 2e, let's say the area of the top and bottom is A. The charge inside is distributed, again, over a volume. So we have A is the area, and then we have the height, which is 2d, and we divide that by epsilon naught. And so, in fact, we see that in this case, we have rho star d over epsilon naught and hat. And so this electric field is stronger at this location. They're all pointing in the same direction there. They all have different symmetries, but this has the greatest magnitude. This is next, and this is last. And so in some sense, this means that the total charge in these universes is different. And so the charge density is the same in all these universes, but we have characteristic sizes of the universe that are different. So if we think of we have a well, let's say we're building this with using Gauss's law with some area here, and so we can imagine having a top surface. The height is 2d, and the sides maybe of the top and bottom are d, and so the sort of the volume that we're considering here, the characteristic volume, goes like 8 d cubed, and we can make d go to infinity, right? So that would be it would be an infinitely large universe, of course, with this value of d going to infinity. In this case, in the characteristic size, the characteristic volume in this case would be, we have a cylinder. Of course, the radius here is d, and to compare with this one, this would be have a length of 2d. In this case, we would have a volume which is it's pi d squared here, and then times 2d the height, so 2 pi d cubed. This is smaller. Then this is a little bit more than 6d cubed. This is 8d cubed, and this one would have the smallest it would just have a sphere of radius d. We would make that go to infinity, 4 pi d cubed. And so we see that this volume is greater than this one, this is greater than this one. And so these universes that have these different symmetries have a different infinity, right? They're all infinitely large, but ultimately this one is larger than this one, which is larger than that one.